In this example, the two masses have the same mass m. The three springs have the same spring constant k. Let's take vectors pointing to the right as positive vectors. Let's start off by assuming that the first mass m is displaced to the right by a distance y1 from its equilibrium position. So its equilibrium position is originally this point here. That's when the resultant force on m is 0. So if it's displaced to the right by an amount y1, then this spring will exert a force on it to the left with magnitude k y1. So the force is proportional to the displacement y1. But since this vector points to the left, it's negative, so we have minus k y1. And of course we reverse this situation. If m1 was displaced to the left by an amount y1, then the force is got by minusing this vector, and the spring will be compressed, so the force on the mass will be to the right. K is some positive constant. Depends on the material of the spring and how the spring is made. So the minus sign indicates that we reverse the position vector for the position of this mass. Now, the second spring exerts a force on this mass, and this situation is a lot more complicated. For simplicity, let's suppose that y2, the displacement of the second mass, is equal to y1, the displacement of the first mass. Let's suppose that m is displaced to the right by the same amount as m is displaced to the right. So y1 equals y2. That means that y2 minus y1 will equal 0. So then the force on this mass due to this second spring here will be 0. Now that makes sense, because this spring will be neither stretched nor compressed. So the left end of the spring will move a distance y1 to the right, but the right end of the spring will also move the same distance y1 to the right. So this spring exerts no force on this mass. So that simple situation makes sense here. Now let's consider another situation. Let's consider a situation where y2 is greater than y1. Okay, so the displacement of the right end of this spring is greater than the displacement of the left end of the spring. That means this spring will be stretched. So this middle spring will be stretched. And if it's stretched, it will pull on this mass. So it'll exert a force on this mass in a direction to the right, in the positive direction. And again, that makes sense. If y2 is greater than y1, then y2 minus y1 will be greater than 0. So this entire force will be positive. Finally, let's consider the situation where y2 is less than y1. So the right end of the spring is displaced a smaller distance than the left end of the spring. In that case, the spring must be compressed, so it will push on this mass. It will exert a force on this mass in a direction to the left. So the force is now in this direction, in the negative direction. And that makes sense. If y2 is less than y1, then y2 minus y1 will be less than 0. So this force will be negative. Now if you stare at this second equation enough and run through the same logic I went through here, you will be able to get the resultant force on the second mass. By Newton's second law, the resultant force on each mass is the mass times the acceleration of each mass. So you should keep in mind that y1 and y2 are actually vectors. They could be positive or negative. I've been talking about them as if they are magnitudes. That's just one particular configuration where these masses are displaced to the right. Then we could think of y1 and y2 as magnitudes, because they are positive vectors then. So we're displacing in the positive direction, but of course y1 and y2 could be negative. If that was the case, then we just reverse what we did here, and we'd still end up showing this result to be true. And similarly for the second equation. Okay, we are going to solve this system of differential equations. we let m equal 1, k equals 2, and we use the following initial conditions. The initial position and velocity of the first mass and the initial position and velocity of the second mass. So big Y1 and big Y2 are the Laplace transforms of little y1 and little y2 respectively. Okay, let's look at the first equation. Plug in 1 for m, 2 for k. So the right hand side here we get minus 2y1 minus 2y1, that's minus 4y1 plus 2y2. Now we will have to get the Laplace transform of a second derivative, so we can look that up here. So we need minus the derivative of y1 at 0 minus s times y1 at 0 plus s squared times f of s. Well, big F of s is the Laplace transform of little f. The Laplace transform of little y1 is big Y1. So the right hand side is straightforward. L of little y1 is big Y1. L of little y2 is big Y2. Next we plug in the initial conditions. Y1 prime at 0 is root 6. Y1 at 0 is 1. So we minus s times 1. Well, that's just minus s. So we bring all the y1s together, so we have s squared plus 4y1s on the left hand side. Bring the minus root 6 minus s to the right hand side. And the plus 2y2s is brought to the left. So we have y1s term, y2s term, and we have the expression on the right hand side not involving y1 or y2. Now I won't run through the second equation, but if you go through it, this is what you'll get. So the next step now would be to solve for y1 and y2. Now in a previous video I explained how to solve a system like this using Cramer's rule, so I won't bother doing it here. We just look at the answer here. Here is the answer for y1 of s. Now as I said, you will get this thing here exactly as it is from Cramer's rule when you evaluate the determinants. Now we can break this into two partial fractions by factorizing the denominator here. You might notice that the denominator here has the form a squared minus b squared, which can be factorized as a minus b times a plus b, where a in this case is s squared plus 4 and b is 2. So we can write the denominator as s squared plus 4 all squared minus 2 squared. So a is s squared plus 4 and b is 2. So we have a minus b. So that's s squared plus 4 minus 2. That's s squared plus 2. And that's multiplied by a plus b. That's s squared plus 4 plus 2. Well, that's s squared plus 6. Now let's multiply out the top. We get an s cubed term from s times s squared. That's the only s cubed term appearing on top. Now let's look at the s squared term. We've root 6s squared here. And, well, that's the only one. And what about the s term? Well, we've s by 4 and we've 2 by s. That's 6s. And as for the constant, we have plus 4 root 6 minus 2 root 6. That's plus 2 root 6. So we get the partial fractions. We have to have a linear expression in s on top for both of these because the denominators are quadratics. So adding these two fractions together, we get this. We just multiply as plus b by s squared plus 6, cs plus d by s squared plus 2. And the numerators must equal, of course. So let's look at the s cubed terms. So we see we have a plus c must equal 1. As for the s squared terms, we have b plus d equal to root 6. As for the s terms, we have 6a plus 2c must equal 6. And as for the constants, 6b plus 2d must equal 2 root 6. Multiply this equation by minus 2 to get this here, and add it on to this one here. 6a plus 2c equals 6. So that gives us 4a equals 4, a equals 1. Now from this first equation, if a equals 1, c equals 0. Let's find b and d, so we can multiply this equation here by minus 2. And that's what I have up here. And just take down the second one underneath it, add them together. 4b equals 0, so b equals 0. And if b is 0, we can see that d must equal root 6. So now we know that this a is 1. We know that b is 0. C is 0. And d is root 6. So now we want the inverse transforms of these. So we have s over s squared plus a squared. Comparing here, we can see a squared is 2, so a is root 2. So we get cos root 2t. And as for this one here, it's got the form a over s squared plus a squared. We don't have to do any adjusting here actually. We can see that a squared is 6, a is root 6, so we get sine root 6 times t. So now we have the position of the first mass as a function of time. So y1 could be positive or negative. As I said already, y1 is not a magnitude, it's a vector. And we can see that no matter how big t is, this thing is not approaching any value. So y1 keeps on changing indefinitely. So we're dealing with undamped motion here. In reality, of course, y1 would eventually approach some value. The first mass would come to a stop. Now, I won't do the calculation for y2, but you can see, of course, for y2, we see that as t increases, we are not approaching some limiting value. So the vibration for the second mass and the first mass continues indefinitely.